at the background, we try to look at computer vision and then the transition from the natural images to our medical image analysis. And then first of all, we look at what is computer vision to even begin with, right? So it's basically an attempt to give computers somewhat similar vision as human beings have, right? So if you look at human beings, we have the vision process involves two main organs: the sensory organ, which is the eye, and then the one which processes the information, which is the brain. So here, if you look at the depiction here, you see that the image takes the data, sends it to the brain, and then the brain processes it. Similarly, when you look at computers, this is the setup. So we have also a sensory device, which in most cases would be some form of a camera. It captures the information, and then we have the brain, which is the CPU or the computer, which then processes it, and then we have some form of interpretation that we can make. Now, the first attempt to define computer vision, we can trace it back to the 60s. And then we will look at a letter that was written by the MIT summer group later when we moved down. But one also significant event in computer vision can be captured in the 1966, where we have these two neurobiologists from Harvard Medical School, and later on won 2 Nobel Prizes. They experimented with the kitten or the cat, right? So what they did basically is to try to artificially blind the cat in one of the eyes, and then try to test what happens to the cat as they grow up. And just a quick point, normally you would see that I put a QR code at the top of some of the pages, and they are links. So if you scan, you get a link to like a web page which talks about whatever the slide is discussing. So in most of the pages, you would see this QR code at the top. So if you want to quickly have a look, you can quickly scan it and then open it with your phone to read something more about it. So if you want to know more about the experiment which was done by these two scientists, you can check it from the link. But basically what they notice is that when they slide or they project certain patterns to the cat, they noted that specific patterns simulated activities within some part of the brain. And then the result was that the visual cortex cells are sensitive to orientations of edges, but insensitive to their position, right? So it means that irrespective of where you put the specific object, it doesn't really make a difference. But rather, if the edges are different, then you get those differences in the visual cortex. So this is just to, and this was the letter I was discussing just in the last two slides, right? So this was in 1966 where this summer project, and then the aim was, if you read the letter, it says the summer project is an attempt to use our summer workers effectively in the construction of a significant part of the visual system. And if then the word used here was pattern recognition. And this is mainly, when you talk about machine learning, it's mainly about recognizing patterns within your data, right? So sometimes you would hear pattern recognition somewhere else, and it's a related topic. So recognizing patterns within your data. And that is what computer vision also does mainly. Now, in this 60s, the computer vision research was born from the MIT summer project. And then about few decades later, we see that we are now having a lot of fields getting into computer vision. So now you have robotics, you have image processing, even biology, physics, and etc. They are all coming together to build a field, right? And then we have NLP, which is now very common with ChatGPT and everything, which is here. All of them riding on the same advantages that we had. Now, going back, so before, let's say, machine learning, we still had some computer vision going on. So computer vision goes a bit further than machine learning itself, right? And so how were they doing this? So basically, you have options, and then what you do is you try to program or model all possible variations of the problem. So for example, if you are looking at cat, then you have to model how are the possible ways that the cat can appear. And this was very tedious one. And of course, it's not possible to be able to determine all the possible variations that can occur and even to understand them, right? So this was limited in terms of application. However, we also see that, for example, if you look at these images here, it's easy for humans to tell which one is a dog, for example, and which one is not a dog. However, machines would find it hard to be able to differentiate this if we are going by the the modeling of all the possible variations. You can't capture all of this possible variations. You can't also capture this. This is another example where you have a dog and then other things which are not dog, right? Another example can also be seen here and this as well. So this was very tedious one, and it was basically impossible to be able to capture everything. So what do we do, right? So this is where the machine learning comes in. Machine learning, you have a lot of data, and then you obviously need some computational resources. And then we try to learn from the data itself, right? So this time we don't say, okay, these are all the possible appearance, but we take all the data and then we let the machine itself learn from this data to know which one is correct and which one is not. And that leads us to the topic of machine learning, right? So you can look at the definitions. There are several definitions for machine learning, but this is more or less the simplified one, so I want to share. Learning is any process by which a system improves performance from experience, right? So here there is performance and then there is experience. And when we talk about experience in machine learning, we are looking at the data that the machine is going to learn from. So the data is seen as the experience which the machine learns from in order to improve the performance. And then we use machine learning, obviously, in cases where human expertise does not even exist. So if we want to go to Mars and navigate on Mars, maybe it's better to deploy a machine than to deploy human, because then it reduces the risk of something bad happening. And then we also use machine learning in cases where humans cannot explain their expertise, right? For example, it's speech recognition, where you can get several humans who would speak several languages, but not a lot, because there are a lot of languages. But then you can train a machine to be able to recognize tons of languages at a time. And then we also have in cases where the models must be customized, right? So we have what we call personalized medicine, where we want to make sure that we don't prescribe one medicine for everybody, but we're able to personalize the medicine based on the person's needs. And then when there are situations where the amount of data to learn from is very huge, that human beings cannot easily learn from that data and make predictions, but machines can do this given enough power and processing power, of course. So these are the cases where we use machine learning. We have four main types of machine learning, or four main types of learning, like how the machine learns from data. The first case, we call it the supervised learning, where we have our training data and then also some labels. So labels refer to what the ground truth to the data that we have. So in cases like that, we call it supervised learning because the machine learns from data where they are ground truth. Then in some cases, there are no ground truth. We only have the data, but we don't have the ground truth. Here we apply what we call unsupervised learning, where in most cases, we then don't have any specific thing we want to learn, but we are only looking at patterns within the data and trying to do what we call clustering. So we just look at the data, we don't have any labels, but we see that, okay, per the features of the data, we can classify this into one group and then classify this other one into another group. So we try to create clusters within the data, even though we don't have the labels itself. Then we have semi-supervised. So semi-supervised is somewhere between supervised and then unsupervised. So with semi-supervised, we have some labels, but not all for all your training data. So few labels. So you do a bit of supervised learning and also you try to apply some ideas from unsupervised learning in there. Then we have reinforcement learning. Reinforcement learning, here we don't have labels. However, we have actions and then rewards. So we have what we call an agent, which takes action. So the agent has specific number of actions they can make given the current state. And then anytime they take an action, we provide a reward. And based on the reward, the agent will now learn that this action I took was good or was not good. So we have reward from sequence of actions. And normally we use reinforcement learning for certain tasks like, let's say, autonomous driving could be a typical example. So where the agent is driving, they have about four or maybe six actions they can take. They can move forward, they can move back, they can turn left and then right. So let's just stick to this four. And then anytime they make a specific action, we reward the agent. And if the reward is high, it means that the action they took was good. And then they try to then maximize the reward based on their environment and the action they took. So normally for autonomous driving machine learning, you would see a lot of people using reinforcement learning for set tasks. So these are the types of learning that we have. And then we can also break down machine learning algorithms into three main components, right? So we have what we call representation, which talks about how do we even strategize the learning process? What do we want to learn? What are the goals of the learning process? So that is the representation. Once we have that, then we try to optimize the learning process. And then the third point is evaluation. So at some point, we need to evaluate and see whether the learning process is going well or not. So we'll look at each of them a bit more into details. What does it mean if we say representation? What is optimization? What is evaluation? Right. So representation, normally we are looking at what algorithm is good for a particular problem. So this is the representation. So for example, there are some cases where we would use linear regression. This is also very common in statistics. Depending on the task, we will use neural networks. We can also use SVMs, that support vector machines. Then so these are for numerical functions. And then we have the symbolic functions where, for example, we use decision trees. So if A and B are present, then we branch to this side. If this is that, yes or no, we branch. So we can create a decision tree to also learn. Then we have what we call the nearest neighbor. So there are some cases that we only are interested in the close by instances of the given data to be able to predict what that data is. And then there are also probabilistic models that we can use. So these are all representations that we can use to learn from our data. And the choice depends on, one, the data type we have, and then also the kind of predictions that we want to make. Right. Now we take an example. If you are looking at supervised learning, right? So still on representation, we choose supervised learning. And then under supervised learning, normally you have two main types of tasks. One is a classification task. So classification tasks here, the prediction we want to make, which is our Y, is normally a categorical label. So for example, we have images, and then we want to predict if this image is a cat or is a dog or is something else. So this would be a supervised learning where the prediction we are making is categorical. So it falls under classification. And here what we do is we have our training data, which is the X and Y pairs. So this means that image is X and then the label is Y. So X1 could be the image of, let's say, a cat, and then the label will be cat. This could be image of a dog, and then its label is dog. And then so we have our data. And then here the assumption. So the assumption is that there exists a function f. So a bit of functional analysis here, but so the assumption is that there is a function f of x which maps our x to our y. This function we don't know, right? This function we don't know, and that is what we want to learn. Similarly, if you look at regression tasks, so regression, the difference between regression and then the classification is basically the value of y. So for regression, the value of y is a real value. So it could be that, okay, we want to train a model which takes your image and predict your age. Now, age would be a real value. So in that case, the task becomes a regression task as against a classification task, right? And it's a similar setup that we would have. So the emphasis is on this function f of x, which is the representation that we want. Now, this f of x, we can represent it here, right? So this x here, and this is our y. We say that our y, we can express it as a parameter m multiplying x plus b, where m and b are like constants that we don't know yet. And the aim of the learning process basically is to estimate the value of m and then the value of b. Once we have this, we can predict our y given x. And if you remember a bit of linear regression, normally we will plot our examples, and then we would have this line which we call the line of best fit in between. So I remember high school, we just draw this line with our eye inspection. However, when you go a bit further, there are ways to estimate exactly what this line should be based on the data that you have, right? Now, in regression tags, we have a way of estimating the difference. So we have what we call the root mean square error. which is this, or we can also use the mean absolute error. So it's basically the difference between our labels and then our predictions, right? So the aim is that when our prediction is perfect, then this would be equal to 0, and the whole of this goes to 0. However, the prediction would not be perfect, so the aim is to minimize the error as much as possible, and that is what the learning process is really about. Then we have a cross entropy error or loss, which is for categorical task. So the question is, how do we minimize this, right? And then this comes in. So there are, if we plot these functions, for example, if you plot them here, then by inspection, we can easily detect that, okay, this is the minimum. And at this point, our error is minimized. That is if our function is a convex function. However, you can have a non-convex function with multiple minimums like we have here, right? And then the aim is to get to this point. However, we can easily end up in any of this point here if we want to estimate. And to solve that issue, we use the the mean square technique in statistics. So just not to bore you, we can actually, in a case of two variables or two independent variables, we can easily estimate our m and b. And then this we can do with a little bit of statistics in mind. However, in most of the machine learning tasks, we have multiple independent variables, and therefore it's not easy to estimate it this way. And that brings us to what we call gradient descent. So where it's not easy to estimate, we have a technique called gradient descent, which kinds of try to follow the gradient of our function and move to the minimum point of the function. And this is the algorithm for performing our gradient descent. So basically, we would initialize our weight, then we compute some gradient, and then we adjust our weight based on this gradient, and then we repeat this process until we get to the minimum or we get to some termination criteria. So this criteria, we said that, okay, if the error is less than 0.001, we stop. Or if something else is this way, we stop. So we do this, repeat this process until we get to this termination criteria. Right, so from there, we look at some metrics. Now, once you've done so we checked going back, we already saw the representation, which is a function, and then gradient descent talks about optimization, which was the second point. And then you have the evaluation. Now, after getting your model, you have to evaluate and see whether it's giving you good performance. And one way to do this is with what we call the confusion metrics, where we try to look at, okay, what are the true positives, what are the false positives, what are the false negative, and what are the true negatives. So true positive simply means that your ground truth says it's positive, and you are also predicting it as positive. So that is the correct, what we say is correct. And then true negatives means that your ground truth says they are negative and you predict it as negative. So when you add this and this together, you get your kind of idea of the accuracy of the model. Then there are what we call the false negative and false positive, which are the wrong predictions. And based on the classification or the task you are performing, you might be interested in one or two of these metrics and not all of them, right?
Giles,
Yep.
So I just thought I think we've run for about 30 minutes.
Okay.
Uh, so I wanted to just check if anyone has any questions, midway that,
Okay. Yep.
they would need to be addressed. Otherwise, we would continue and then do the Q&A session at the end of the presentation.
Yep. Yep.
So please, if
So
you have
yeah,
any questions,
if you have any
post in the,
question,
yeah, post in the chat, and then yeah, we'll add you on stage. Otherwise, we'll just continue with the presentation and address all questions at the end of the
okay.
session.
Yep. So you have an idea how many people we have in the backstage now?
Oh yes, yes.
Okay, great. So I think because of time, I'll try to move a bit faster because there are a lot of slides left. Right. So I
So
mean,
the
based.
hold on. So
Mhm.
there are a few questions here. So Christina says that yes, thanks for the presentation so far. She would love to learn a bit more about applications and use cases. So
Yes.
I think you have that, but it's probably at
Yeah.
the end, right?
Yeah.
So
So that would come, Christina.
right,
So thanks. Yeah.
yes. And I think in a test, I think from Batra, Shubhangini Batra. I hope I pronounced your name correctly.
Yeah.
So I think the question there is
In
uh,
a test,
in it,
how can you calculate number
the
of
number of false
false
negatives, exactly.
negatives? Yeah. So the number of false negatives is depending on your data types, right? So the false negatives basically it's you compare how many negatives did you predict which were positives, right? So you take your ground truth, you take the positives from your ground truth, and then you compare it to your prediction. How many of those positive did you predict as negative? And that is basically your false negatives. So it's a comparison of your ground truth and your predictions that gives you those values. I hope it's clear.
So I
Um,
think most people are really looking forward to real world applications.
yes, we will get
Um,
there.
exactly. So as Gal said, I think he has that in store. So please be patient with us. Yeah, that will come soon. Thank you. Are there any further questions before we proceed?
Yeah, great. So
Uh,
let's move on
yes,
maybe to the
please go on.
interesting part. Yeah. So based on the this confusion matrix, you can compute this metrics, which normally is used a lot in medicine, right? What we call sensitivity and specificity, right? Especially these two metrics. So here, if sensitivity is basically a ratio of your true positives to your true positive plus your false negatives, right? And then specificity is your true negatives divided by your false positives and true negatives. So when we talk about sensitivity in medicine, it's basically looking at the rate at which we detect true positives. So if your model has a higher sensitivity, it means that if somebody has a specific disease, for example, then it is hard for your model to miss that person and say that the person doesn't have the disease, right? So sensitivity, depending on what the prediction is, it's very important when it comes to medicine because we want the model to be able to detect when somebody has a disease. For example, if it is cancer, we want high sensitivity. So high sensitivity means that the software or the model doesn't easily miss. Because when you miss somebody, if somebody has, for example, a cancer and you miss it, it's very dangerous. So in medical application, we want very high sensitivity. And then when we talk about specificity, it is somehow the opposite, right? So we are looking at what is the probability that somebody we say has the disease truly has it. So how specific is it that if your model says that somebody has a cancer, the person really has the cancer and not a false positive? So that is the specificity. And normally you use this to evaluate the performance of your model. And based on the use case, you can say that, oh, if I even get 90% sensitivity, I'm okay. Or if it is something which detects very crucial disease, then you want very high sensitivity. So all of this comes in when you want to evaluate your model. Then there are other metrics there that also has their own use cases. Now let's move a bit back and then look at some applications. Now pre-2012, right? So from 2012, that is where we have a lot of deep learning coming in. But before that, we still had machine learning, but they were mainly done through this step. So you get your input, you do what we call pre-processing, right? And pre-processing would then lead you to this what we call feature extraction. So there are different types of features we can extract from the image. We put a learning algorithm, which can be SVM, random forest, or artificial neural network on the extracted features, and then we get our prediction. So we see that here, this feature extraction is very important because if you get the feature wrong, then it's possible that you will not get good result. So this was before 2012. And then post 2012, this is where the magic box came in, right? So here you have your input image. Straight away you give it to your machine learning or deep learning algorithm, and then it gives you the label. And what happens in here is all of both pre-processing, feature extraction, and all of this put together in our machine or deep learning algorithm. So it extracts the feature by itself, and then everybody instantly became a magician. That just give me your image and I tell you what it is, which is good. Now we look at some examples of computer vision tasks, right? Maybe it get a bit interesting moving from here. And one of the oldest tasks is this prediction, the handwritten digit prediction by the National Institute of Standard and Technology. Here we have like images of numbers from 0 to 9, which were handwritten by people. And then the task is to predict which number is in here. We have a total of 60,000 images, each of them very lightweight, 28 by 28 pixels. And then we predict. Now with machine learning, we can go as high as 99.5% accuracy, which means that if you give it 100 image or 1,000 images, you would get maybe 5 of them wrong, which is very high. And at this point, the interest was, if I give you an image, what can I see in the image? So if this is why I put the title here, what can be seen in the image? Right after this was these two data sets where one of them has 10 classes. So you give the image and it tells you which what object can be seen in that image. So still we are looking at what can be seen, right? And then we had another example or another data with over 4 million images and over approximately 1,000 classes. So the task is becoming a bit more and more tedious. But even with that, with machine learning, we are getting over 99% accuracy, over 90% accuracy in here. But all of these are not medical images. They are what we call the real world images, right? Then we move from what can be seen in the image, and now the interest is we want to go beyond what can be seen. We also want to know where in the image can we see a specific thing, right? And that leads to different types of tasks. One is the semantic segmentation, where we segment different objects within the image. Then we also have what we call localization and classification, where we now put a box around the object. So similar to object detection. So we detect dog here, cat, and then we try to segment these instances. So success in one field, we try more and more challenging tasks. And all of this, we had a lot of successes. But I would pick what we call the ImageNet. ImageNet is basically this 1,000 classes images, which was very hard. But after 2012, where we started applying deep learning approaches, we see that the error, which was initially about over 25% error, started reducing, right? And then it's keep reducing to less than 5% error as at 2017, with the top 5 error on the ImageNet. And what was the reason? Very simple. If we compare these two networks, one from 98 and one from 2012, we see that this deep learning network is a bit shallow. So the word is shallow as compared to the one down here, which is a bit deep. So basically, we are saying that with deep learning, with improvement in computers, we are able to build a bigger model. And with the emergence of GPUs, we are able to train these models faster. And this leads to increase in performance. If you compare these two, um, models, right? And this is where big data, hardware, and deep comes in. So we have the models are now better because we have a lot of data, and this is very important when we come to the applications in medical field. And then there is hardware, and then the models are now more complex, and then they help to boost the performance. Now, with all these successes, we now move to medical image analysis. So drawing inspiration from real world applications, real world images, we now try to apply this to medical image. Now, I would want to draw a comparison between, for example, real world image and then this medical image here. So the first difference you would see would be the resolution. So this is 28 by 28, and most medical images ranges between this voxels. And on computer, this is less than a kilobyte, 800 bytes, for example. But this is 240 megabyte. So immediately you see the difference between real world image and then a medical image. And then one thing which comes to mind is increased memory and CPU consumption. So when you are dealing with medical images, the first challenge is that now you have images which are huge, cannot easily fit into memory. And then because they are also huge, whatever computation that you would do here is increased exponentially. So this is the first challenge, increased dimension and resolution. And to address this, so this is just the next step in applying deep learning to medical image. In addressing this, several people have proposed solutions, right? So the first solution is that, okay, even though medical images are 3D in general, right? They are 3D in general. However, the 3D, we can still get slices of 2D images, which is making up the 3 dimension. So what we do is, okay, let's apply our methodology on these 2D slices and then later on stack them. So that is like first approach, or the most reasonable thing to do is to do this 2D, because from our previous knowledge is 2D that we know how to handle. And then in order to improve this, we have what we call 2.5D, which is, now we don't just take a slice, but we also take a slice plus the one or two slices below and above it, and then use that to make our predictions. And this is what we call 2.5D slices. All of this work. However, the problem is that we lose 3D context information. So there are certain things that you can only predict them well if you have the full 3D information. For example, if you are predicting an organ, looking just on one slice, it's not easy to predict what organ it is if you are just looking at one slice. So these approaches lead us to the problem that we lose 3D context information. And as a way of proposing a solution, we have what we call crosshair filters, which basically what it does is, instead of using a 3D convolution, sorry if you don't know what convolution is, maybe I moved a bit one step forward, but yeah, it's basically a way of extracting information within a given region using convolutional filters. And normally you would do a 3D convolution, which is a bit expensive in terms of memory and then computation. But we can get the same information if we have what we call a crosshair filter, where instead of doing a full 3D, we get informations along the diagonals of the region. And this hopefully would give you the same information as you would get in a full 3D. This is a paper I worked on with this methodology, and I'll talk about it a bit later down there, and also provide you with a link if you are interested to read more about this approach. But this is one way of handling the problem regarding the consumption and then the computational problem. And then here we then look at also one big problem with medical imaging has to do with data. So in most cases, we know medical data has a lot of privacy issues and legal issues, and therefore in research, it's not easy to, one, get data, and two, to even get the labels, what we call the annotations for those data, the ground truth, is another task. And one way to solve this issue has been to resort to what we call synthetic data. So for example, the image up here, this is the real data, MRA data of the head. And this here is a segmentation of the brain vessels within the data here. And an attempt to simulate this, we generate like a synthetic data. And this was the vessels in that data. And then we can see that they look similar. And what we do is we can then train our models on this synthetic data and then apply it to the clinical data we have up here, and then try to see how the performance will look like, because then you don't get a medical doctor to do these annotations for you. It's a lot of time and effort. But this and everything is in one paper, which I will share the link. And if you want to read more about it, you can check later on. But now let's come back to in real world images. We looked at what can be seen and then where it can be seen as two main examples. So under medical images, we would consider one example regarding what can be seen, one research on that. And we will start with what we call collateral flow grading. So this is a research I was involved in. And basically what we want to do is this. In cases of stroke, for example, when a blood vessel is blocked here, then it's not possible for the blood to flow to this region in the brain, right? So that region loses oxygen, and then the cells in this region start to die, right? What we call infarct. Now, in some cases, there would be other specialized vessels in this region which can supply oxygen to this area where the main vessel cannot produce or supply oxygen to. Now, this supply of oxygen or nutrient to this region is what we call collateral flow. So basically, what it means is that the main flow of blood is not getting to that region, but we can get other collateral circulation from those regions around it to support that. And when that happens, if you have a good collateral flow, then you have a good chance of recovering, or there is likelihood of successful reperfusion, what we call reperfusion, where the person, that region can regenerate and then the person can get a favorable clinical outcome. So this collateral flow is very important. One, if you have good, like I said, it helps to sustain that area during the stroke attack. And then two, it's also it's a factor of how successful the outcome would be, the clinical outcome would be. And then also, it's also one factor which determines which stroke care model is chosen. So should we transport the patient to another facility or should we treat the patient immediately? Now, in normal clinical routine, when the patient comes in, they have to take these images, we call them DSA, digitally subtracted angiography. They have to do this imaging, and then a doctor needs to then manually scan through the image and then check whether the collateral flow is good or not. And this can take some time, which is in stroke situation, every minute count. So this is very tedious and can, by the time they determine that, okay, the collateral flow is good or it's not good, you would have already lost some time in doing that. That is one, time consuming. And two, because the image, the decision whether it is good or bad is based on which clinician is looking at it. It's very subjective. In most cases, an experiment we did shows that there is what we call inter-observer agreement of just 16%. What it means is that if you put two clinicians or two doctors in a room, and then you give them 100 images to grade whether it's good or not good, they will only agree 16 out of the 100. So these two main things mean that there is the need for automation. And what we try to do is to automate this process, this grading process, so that the doctor doesn't have to decide. There would be a machine learning model in between. So this is what we did. We have these images coming from what we call MR perfusion images. So when the patient comes, these images are first taken, right, before the digitally subtracted image. And then the idea is if these images are taken first, then it is better if we can even make the prediction from these images so that we don't need to do the follow-up DSA images. So we have these images as our input. Each of the images have three parameters, what we call time to peak. So time to peak is basically they inject something into the blood vessel and they time it to see at what time will that agent get to certain regions of the brain, and that is the time to peak. Then you also have the relative blood flow and relative blood volume. With these three images from the patient, we want to predict whether the collateral flow is bad, whether it is medium or it is good. And that was the experiment we wanted to do. So we start with our representation, as we saw already. So how do we represent the problem, right? So we try several approaches. So one of them is to first detect which region, even in the brain, is suffering from this occlusion or suffering from the blockage. So that is the first step. And here you use reinforcement learning to do this detection. So I already explained a bit what reinforcement learning is. So it is kind of whenever you want to navigate something, it's reinforcement learning is a good start. So we use reinforcement learning to learn which region of the brain is suffering from this. And once we take that region of the brain, we extract features from it, right? So we do feature extraction, and then we now have a classifier which takes these features and then predict whether it's good, medium, or bad, right? So this was the proposed pipeline or representation that we had. And then these were some of the results, right? So we look at cases where we predict the three classes straight away, and then cases where we put two classes together, and then we do one prediction and then another prediction on top of it. And here we had about 70% accuracy. Maximum, I think it's 72. Yeah, in the cascaded case. Which one, first of all, based on 16% inter-observer agreement, 72 is way better comparing it to the clinician's prediction, right? So what it means is that one, even the data itself, because we have 16% inter-observer agreement, what it means is that the data we are even using to train, we cannot be very sure of the data because whoever labeled it might also get it wrong. And these are some of the challenges in medical imaging, where if you have very low inter-observer value, then you cannot even be sure of your ground truth labels to begin with. And there is therefore the need for a standardized data where people can use it to train the model. But this was just what we call like a preliminary experiment, and then an attempt to prove that doing this automatically is possible. So 72% is okay. However, the recommendation is that we should have a follow-up experiment where we increase the data size because I don't know whether, okay, I didn't state the amount of data here, but it's not a lot. I think it's less than 200 patients, where we can get more patients and try to improve the model. Right. So again, if you want to read more about it, you can scan the QR code because I think somebody was asking. Whenever you see a QR code up here, it's normally a link to either a paper or a web page where I'm discussing. So you can always scan it on your phone, and then you can have a look at the paper that I'm discussing. So here, it's a classification task. So just to note, we want to classify what is seen in the image, right? Then we look at where can it be seen. So under where can it be seen, you have what we call detection or localization. We also have labeling, we have segmentation. So we look at some few examples of experiments in those areas as well, right? So the first one is liver and lesion segmentation. So in this particular paper, if you can scan the QR code, here we have CT images, right? And then the task is to segment first the liver, and then this region, which is the lesion. So it's those regions which are the lesion, right? So here there are a couple of them in the liver. And this, there is even a challenge, a segmentation challenge on this particular data set in the group, where every year people bring in improved models, try to do this. So this paper talks about that. And in the image, you see the yellow regions are the wrong segmentations, and then red regions are also wrong lesion segmentation. And then green is the correct liver segmentation, blue is the correct lesion segmentation. Right. This I just present one slide on it, and then we look at the result quickly. So the paper itself um, proposed what we call a cascaded unit plus a 3D random forest. Was it random forest? Yeah. And here you look at different results in with different. So normally in these papers, what you do is once you propose a methodology, you try to compare it to existing methodology, and the idea is you want to improve the performance. So in most cases, the proposed methodology would give better performance than the existing ones. Otherwise, it's hard to publish. So yeah, so this is segmentation. So another example of AI or um, machine learning task in medical imaging. Then we look at this other task, which is vertebral labeling. So here, the first one, we did segmentation. Here, we want to label the vertebra in the human body, right? So this paper was a bit involved also. And basically, we have a CT image, right? And then there is this network, which we call the butterfly net, which takes in the image in two different reformations, tries to predict heat maps, and also label the different vertebra within the spine. So this is an example of the ground truth. Maybe if you don't already know anything about the vertebral labeling, it might not be interesting. But so there are different regions within the spine, and this labeling, one specific application is, for example, during surgery, right? So when you have a fracture or anything, normally the surgeon will need to know which of the fractures, which of the vertebra is fractured, and they need to know exactly this with their labels, right? So we have the the C1, C2, C3. We also have the
Giles,
T.
apologies for the interruption. So we really want to apologize. I think we're about 2 minutes to time, but we still have a lot of content to cover.
Yes,
So
unfortunately.
if it's not a problem for you, we
Yeah,
would definitely
I can.
like to continue. If you have sent us an email, if you registered for meetup, we have access to your email account, and then we will send the slides as well as link to our YouTube channel, so you can watch if you are not able to stay for
Yeah,
the next couple of slides.
yeah,
We
but
do
I
sincerely
think I
apologize.
would, at this point, I'll try to run through a bit. I think this here, the examples may be a bit interesting, and then from here we go to the startups, few startups which are in the AI medicine, medical imaging field, and then yeah,
No, you can take your time. We are recording it anyway, right? So
okay, yeah,
we'll share it then, and
Mhm.
to folks who are able to. We have access to your email if you registered for the event. Otherwise, please inbox me your email, and I will we'll send all the information. So all the information are sent via email. No LinkedIn, please. Yeah. Thank you.
Yep. Thanks. So I think there are few questions.
Guys, I think we can.
Yeah, we take
Uh,
this afterwards, maybe. Yeah.
yes.
Okay. So this is, for example, the ground truth, and then these are different predictions from the data, and then this, for example, is butterfly net at certain with certain variance, and this is another butterfly net. And then at the end, we have different metrics somebody was asking. I don't have all of them off head, but then if you scan this, you could easily get the description of all these metrics. But I think, for example, this is the rate at which the percentage of the IDs which are detected. This mean is the distance, the mean distance, and this is the mean, the standard deviation of the distance. Yeah, and then the next task is like several things put together, deep vessel net. So this is the paper I was discussing in the beginning, and here the idea is to segment the vessel, the brain vessels, and then also um, detect or predict the center line, those the center of the vessel, and then what we call bifurcation. Bifurcation is basically the point where the vessels separate into two or more mini vessels. So at that point, we say we have a bifurcation. And then also predict the radius of the vessel. And here we have several data sets. So this is the clinical MRA data that I already showed you. This is data from a mice brain, and then this is our synthetic data we generated. So the idea is to retrain on the synthetic data and then apply it to the human as well as the mice, and then try to see how the performance would be. And here we have um, our proposed methodology scoring over 96% in dice. So dice, it's normally in segmentation tags we assess it based on what we call a dice score, or in some fields they call it F1 score, which is kind of like it's a bit of like, not exactly, but equivalent to what we call intersection over union of the segmentation, but not exactly that. So here we have higher die score for this compared to other existing machine learning methodologies, and this is because we use this crosshair filter that I was describing in the beginning. Now, we've seen few research. This is not exhaustive, like I said. I just wanted to pick few of them so you see, you have a feel. But the most important thing is translation. So how do we link this research to the clinic, right? For example, for us researchers, this is how we do our research, right? So we are writing code, we are executing code. But for the radiologist or the clinician, this is normally their workflow. So they get a request, they schedule an image, they take the image, they go sit behind their PC, interpret it, write a report, and then there is a follow-up care if needed, right? So the question is, how do we push all this here? And one place to do this is between the image acquisition and then the interpretation. So this is where our models need to sit. So when they take the image, before they come to interpret it, we want to either do the interpretation automatically, which is one option, or we want to make this interpretation task as easy and efficient as possible for the radiologist or the clinician. And if you are able to fit well within this, between these two steps, this is where you make your money, right? So we are going to look at few startups who are doing this. But before we do that, even in the
Giles,
research field, yeah.
I think you there was a little bit of an issue with your network, so if you
Ah,
can come back maybe 30 seconds. Yeah.
okay, sorry. So what I was saying is that in most cases, this is how researchers do their research, right? So they are mainly sitting in the lab, writing code, executing training models, etc. And then this is the workflow of the clinician, the radiologist. They get requests, they schedule it, they take the image, they interpret the image, write their report, and then there is a follow-up. This schedule is so tight that if you are bringing anything into this, it has to improve their work. And one way to do this is either we fit in between the image acquisition and then the image interpretation, right? This is where we want to fit our model. And we have to do it either automatically doing the interpretation or enhancing the process. To do this, also on the research side, though, we worked on a tool we call Brad's toolkit. And what this toolkit basically does is it takes MRI images, apply already existing segmentation models to this, and try to create a software which helps the doctors to easily do this segmentation and labeling, right? So here there are a few steps in between, and normally researchers in our field, they are very good in the research side, but linking to the clinic is a problem because to do this you also need some software engineering knowledge to be able to know all the integrations and etc that needs to happen so that you have a good software that the clinician can use, because they don't want to see any code, they don't want to see anything like we do. So you need a good software guy or software engineer to do this. And we tried this in our group, created a software. You can look at the paper also on this software here, which tried to fill in. But this was specifically for only this task, which was the segmentation of how do you call it, tumor within the brain from this data. So this was the first step. We have a paper on it if you are interested. And then there is what we call DCM. So DCM means DICOM. Normally the images you get from the scanners are in DICOM format. And this work is not yet published, so I put not published here. However, this is like the next level that we want to go, where researchers would have some kind of a software which makes it easy for them to at least test their models in the clinical setting. So you don't only be in your lab doing research and you don't know how it's going to even perform when you send it to the clinic. So we are building like a tool, or let's say a software, which already takes care of the image coming from the scan, everything, all the workflow. And as a researcher, all you need is to plug in your model, and then every other thing in terms of software and everything is handled for you. So here we don't provide a model, but we are only providing the framework. This is something we are working on, not yet published, but we are going to make it open source once it's ready, so you can easily install it. And then the idea is to have like a marketplace where researchers can publish their models onto this marketplace, and then anybody around the world can set up this and then easily install different models. For example, brain segmentation model, spine segmentation model, tumor segment, anything easily within the clinic, and then for research purposes test these models. So this is something we are working on now, not yet ready. Now let's look at some startups who are in this area. So those people who have already figured out this translation, and then they have a startup for their solution. And there I will start with first showing you an overview of, we have quite a number of them in the DACH region. So DACH region is basically Germany, Austria, and then Switzerland. So these are some of the startups in the DACH region. But to go into more details, I would start with my own startup here in Munich, where we do osteoporosis screening. And so basically, in layman's language, when we say someone has osteoporosis, it's kind of means that there is the minerals in the bone is reduced, and therefore the bone is very porous and can easily break. So normally what happens is when you have osteoporosis, the little mistake, if you even twist your hand or anything, it can lead to fracture of your bone. And in per statistics, 1 out of 3 women would have osteoporosis in their life, which is very high. And then 1 out of 5 men would experience this. But if we look at, so our motivation is that in the diagnosis, there is what we call a diagnosis gap, in the sense that when osteoporosis leads to, let's say, a fracture, we spend in Europe, we are spending over close to 60 billion euros on the treatment of those fractures and things resulting from osteoporosis. Meanwhile, we are spending only 1.6 billion in terms of prevention or screening. And this is the gap we want to close as a startup, where we make screening of osteoporosis very simple and easier. And then if we even look at in cancer situation, because some of the drugs used in treatment of breast cancer and prostate cancer, they have certain chemicals in it which even makes the situation worse. So in breast cancer cases or prostate cancer cases, we now have 2 out of 3 women developing osteoporosis and 1 out of 3 men developing osteoporosis. And this is a huge thing which needs to be solved. Now, per our research, we realize that in most cases, people, for example, would have CT scans lying around. For example, you feel some pains in your abdomen, and then you go to the clinic to take a CT scan. And what Bone Screen, our startup, does is when you take a CT scan for whatever reason, provided your spine region is in the CT scan, we extract information which helps to determine whether the person is osteoporotic or not. And this is what we call opportunistic screening, where you use data for something different from the intended purpose. And this helps to reduce or detect osteoporosis in cases where it would have not been detected. So we basically sit between the scanner and then the PACS. The PACS is what the radiologists used. And what we do is we process the data, we provide report to the clinician, and then they can be able to diagnose osteoporosis. Basically, what we do is we do segmentation of your spine. We're able to detect if there are fractures, for example, in this case. And then we're able to tell where, for example, you see red means the person is osteoporotic. And where there are a lot of green, it means the person has a normal BMD or bone mineral density. So that is what we do at Bone Screen. Then I also pick one startup called Context Flow. And here I only talk or speak briefly about what they do. So basically they have a software which for chest CT, And then this integrate directly into the hospital system. And what it does, it's used to detect liver nodules within your liver. And then they push this information back to the clinician. The difference here is normally they have like specific CT that you have to, they are required to take in order for them to do this diagnosis. But it's also an example of a startup working within this area, right? Then finally, we have what we call Deep Sea. So this is also another startup. And here, Deep Sea, they provide what we call like a framework. So similar to the one I said we would publish later, they provide a platform which already integrates into the hospital system. And then it allows for different models to be integrated into the hospital system. Some of them are their own models. They also integrate third-party models, and then they provide a platform. So you would find like maybe different models for segmenting liver, spine, blah blah blah, all in one solution. And for example, we in Bone Screen can also integrate into their infrastructure to already reach hospitals who are using their system. So that is for the real world examples and startups. Now, just as a conclusion, already time is spent, but to conclude, there is just one question that I would ask, or I want everybody to also think about is what should be the goal of AI in medicine or in medical imaging, for example. Is it that we want to have a human level performance that, okay, we have a model which can perform as well as humans, or do we want above human level performance? So when do we say a model is good? Is it when it performs like human or when it performs better than human? Right? And to help answer that question, let's look at this table here, right? So let's look at radiologist density by continent. So we take some continent and we look at radiologists per million of the population. We see that in Europe, in North America, but let's, for example, look at Africa here, right? This simply means that there are less than 5 radiologists to a million population, right? And then just note that down. And then let's look at the medical image analysis startups also per continent. And we still see Africa doing poorly down here too. And then finally, let's look at VC funding in medical imaging. And then we see 4.5 million versus billions of investment in there. So now if we put this information we have, and then we go back to the question again about what do we want, right? We can then say that depending on where you find yourself in the world, you would either look for above human performance or not, or just human performance. So in cases, for example, in Africa as a region, where we only have less than 5 radiologists per million, it means that if we are able to even get human performance and say that, okay, our models or our AI can perform as good as human beings, then it's good enough to bring them into clinical practice because we don't have the humans to do the work, right? But if you find yourself in Europe, in North America, where you have considerably a good number of startups, etc., then you can then look for more and say, that, okay, for us to accept AI in medicine, we need the AI to perform better than human beings. And that is the crossroad. So I think the take-home message here is, if you are an investor, there is a lot that can be done in Africa, right? A lot in terms of medicine and AI, because this is the place where we don't have a lot of radiology. This is where we need AI, even more than Europe and North America. And this is the situation we have, that less than five, only two startups per my research. And then we have less than 5 million investment in this region. So that is just the conclusion I want to bring to everybody's attention, and then start the discussion.
Wow, thank you so much. Thank you so much, guys. This is an amazing presentation. I think we've passed the time, but if
Yeah.
there are any questions from the audience, we can add people to the platform right now, and you can also alternatively post your questions in the chat. I think Joe C posted a question earlier during the first round, but we couldn't
Okay.
address it. I think it had
Let me
to do with
refresh
X-ray.
this.
Yeah, so he was asking if you can give an example of how the actual function is described, example for an X-ray diagnostics of a fracture. So how many and which imaging parameters would it be would it use to test input? I'll just
Okay. So
do you see
for
the question?
fracture detection, for example,
Mhm,
can you give an example of how the actual function is described? Example for an X-ray diagnostic of a fracture. How many and which imaging parameters would it use to test input? Okay. Yeah. So for example, if you want to predict fracture from X-ray, right? So you have your X-ray images. Normally, you would have one image per patient. However, there could be multiple fractures, right, within that specific patient data. So what you do is you build your model in such a way that it's able to detect these multiple fractures. And one way to do this would be one to first have like a cascaded model where you first predict or you detect the region of interest. So the region of interest, for example, could be the spine, right? So you detect the spine. So this would be like one. So normally in the software, you will not have one model. It could be multiple models doing different things at different stages. So you could have one model which takes your function itself is your image, your X, and then you have series of layers within your model, and then your prediction will then be let's say 0 1, where 0 is no fracture, 1 means there is fracture. So this could be like the first step. Or you can have different layers of, so if, for example, fractures, we have very severe fracture, we have like minor fracture. So this could also be different classes that you want to predict. So this is how you would do the presentation, right?
I think he came back. He said, uh, there you go. Expanding on my question, back to the slides where you mentioned pre 2012 and
Mm-hmm. Yeah. Um, let's see if I can find that. Mm-hmm. Yeah, I think it's here. How does it look? Those functions, how does it work? Yeah. So in if I would come to the function, yeah, here, right? So for example, this, right? Now your image will be X. And this could be a bit confusing at this point, but image, for us humans, we see image, but for the computer still sees some numbers, right? So it's basically a matrix. If you already done a bit of, I don't know, but we have a matrix which would be as big as the size of your image, right? So you have a matrix, which is your image X. And then, for example, your Y would then be a vector, which tells you that, okay, there is this number of fractures at this position or that. So your input X would then be a matrix and your Y can be a vector. And then the whole f of X will now be like a matrix function or a vector function. So I don't know if that explains it well.
Yeah, I think there's another question from Moyo.
Yes. Do you think we do require a lot of pathological images, bank of images adopted by the model to start accurately pathology? Yes, so this is good question. In deep learning, one key thing is data. So you need data a lot, yes, but also a lot is relative. So the question that you might ask is what is the number, like rough number? And it normally depends on one, the task you are doing, how many labels are you predicting. They all lead to decide how much data you need, right? But yes, you need a lot of data if you would get a good model, because the deeper the model, the better it predicts, and the deeper the model you have, the more data you need in order to train that model, right? So we are talking about maybe tens of thousands or 70,000, hundreds of thousands of data. So it depends on the task that you are performing. But yes, you need a lot of data if you want to make your model perform better. Yeah.
I think there's one more question from Pawan. Yeah, I think if after
Okay.
this we do not have any more, we can proceed to
Yeah.
end the session. Thank you.
Yes. So I will just go back. You asked a nice question, right? Good. So the question was, how do you apply reinforcement learning in collateral flow, blood flow imaging? What is the reward function and how is feedback? Okay. So here we are. Let me use the next image. Yes, here, right? Now we want to detect this region. So this is what the reinforcement learning was for, to detect the region where the stroke has occurred, right? So basically we start with a random box, which could be down here. And then we can take actions by moving up, left, right, or down. So these are the 4 actions. So we have a rigid box moving in 4 directions, for example. In 3D, it's more than 4, but just 2, because you can also move in the other direction. So let's say for simplicity, we have 4 directions. Now, whenever you move the box, we calculate the distance between the new location and the expected location here, right? So if the distance has reduced, we can then give a positive reward or weighted reward, whatever we want to. So the reward is basically depending on the how close are you to the ground truth or the ground truth bounding box. That is how we calculate the reward. And then you have your state, which is your image. And then we try to also use like history of the locations you have already been, so that it doesn't have to go back and forth. So like in a simple sense, this is how the reward function is designed, based on the distance between the current location and then your target location.
So we have one last question from Misha. Putting up on the screen.
Okay. So, based on your experience, example with bone screen with Brad, do you think that we as the industry need to develop highly focused models, one per disease trained on those specific data sets, or in a vein similar to LLMs, large foundational models could be built, which could be applied to many different imaging situations? Same model making prediction for osteoporosis. Okay, yeah, I mean it's an interesting topic that you mentioned, like having similar thing like LLMs, right? But the challenge here is that, in this area, medicine, one, regulations are very stringent for good reason, and currently this will not even be possible. That is one. But assuming it's possible, the question would be that this would be like very huge model, would be hard to train because then you would need a lot of data to be able to cover a lot of different disease areas and etc. And then at the end, the question would be that what would be the gain, right? We can have something for maybe general practice, but for specific disease like cancer and etc., wouldn't do something like that because one, it is very high risk. Because if LLM model gets some translation wrong, this is fine. I mean, but with the AI application in medicine, if something goes wrong, it can lead to somebody dying, and therefore it's a bit tricky. Yeah.
Right. Thank you so much, Giles. I think this was the last question for the day.